Well, goodness gracious, we're on to chapter 12. Maybe I shouldn't say goodness gracious, maybe I should say goodness of fit. Because guess what? That's what this GOF stands for. We're going to get into chapter 12. The first part of chapter 12 deals with these things right here. It's chi-square. It's a chi-square test. It's pronounced like chi, not chi or chai, it's chi. And this, today, our type of them is the goodness of fit test. Hopefully, as we get going, you'll understand why it's called goodness of fit. So here's my example. It says Carrie made a 6-sided die in her ceramics class and rolled it 90 times to test if each side was actually equally likely to show up. Because you want it to be equally likely, otherwise it's a weighted die. The table summarizes the outcomes of her 90 rolls. Is Carrie's die fair? Well, we're going to end up using this chi-square goodness of fit test to test it out. So before we do that, though, I want to think about what it should be, right? If it was an equally likely, out of 90 rolls, 90 divided by 6 gets you 15, right? 90 divided by 6 is 15. So theoretically, each one should have been rolled around 15 times. And it's never going to be perfect when we're doing simulations. But our observed frequency, I'm going to say observed, is clearly not the same as the expected. So the expected would be 15 for each, right? One of them was spot on. The 6s had 15. Everything else was a little bit off. The 2 had a lot. So the question is, are they equally likely? We're going to get into this thing called the goodness of fit test. So let's talk about it a little bit. How can we tell that it's called that we're going to do a chi-square goodness of fit? So there's a couple indicators, and we'll show a few different examples of what it might look like. So if the data is categorical, qualitative, in this case, like fitting into a category, how many were rolls of 1, how many were rolls of 2? We're not like finding an average of it. We're just like, how many fit into that category? Then it could be chi-square goodness of fit. There's one variable in this case. So we're going to get into some other chi-squared that might have 2 variables, multiple variables. This is just the one variable is the outcome of the roll. And from one sample as well. If those things happen, and we know it's going to be a chi-squared distribution, we think it's going to be a goodness of fit. Now, since we're testing something, we're going to do a lot of similar things to like a lot of the similar steps to other inference procedures, like stating hypotheses. So when stating hypotheses, I typically go with this route. This isn't my normal choice. Just using words. So I might say the distribution of blank is the same as blank, right? So I could say the distribution of dice rolls is the same as something, or actually I'm going to change that. I'm going to say all die outcomes are equally likely. I think that's easier to say. Or all die outcomes are not equally likely. But if it doesn't work that way, it could be like a specific distribution. It should be, I could say the distribution of rolls are the same, are equally likely. It's just yes or no essentially for that. But if I didn't do it in words, I could do it in symbols, and I could say like the probability of rolling a 1 is equal to this, the probability of rolling a 2, or saying that they're all equal to each other. And then my alternative would be that like at least 2 are not as claimed. But the problem with that is then we have to state all of the different parameters. So if we're going to avoid that, let's avoid that. So we're going to go back. I'm going to say for this one, since this is the data that we have, I'm going to start off by stating our hypotheses. And I'm going to say my null hypothesis is that all die outcomes are equally likely. I could say are all 1/6 if I wanted. Something like that. Right? Because that would be a fair die. My alternative is that, Oops. Maybe it's not. So all die outcomes are not equally likely. It is a not fair die. There are my hypotheses. Now we're going to work off of those. Okay? Like with other tests and inference procedures in general, we need to check conditions. So we want to know if there's random sample from the population. In this case, it is a one sample. We also want to check for independence. So these two things are the same. The only thing that's different is we're not going to have a normal looking curve. Okay? And I'll show you the picture of that here in a second. So we don't need that. We just need to make sure all expected counts are at least 5. So all expected accounts are at least 5. Otherwise, if it gets too low, and we're going to look at the lowest expected count, then it can mess things up here. But I want to look at what does it look like. So the chi-squared distribution, they're a family of density curves that take only non-negative values. So we're never going to have negative values. We'll show you the formula for it in a second. So it's always going to be skewed right. Always going to be positive. It could technically go like to infinity. It just can't go to infinity on the left side. It goes from 0 to infinity. But it's heavy in the lower values. So that's why the shape is going to look a little bit different and skewed right. So a particular chi-squared distribution is being specified by giving its degrees of freedom. We need to have that. For goodness of fit, use the degrees of freedom of the number of categories minus 1. So we'll get to that here in a second. But you can see here, the degrees of as the degrees of freedom changes, it looks more or less skewed. The higher the degrees of freedom, the farther that middle is moved to the right. But it's always going to be tailing farther to the right because it could go on forever. A couple notes about chi-square. The mean of a particular chi-square distribution is equal to its degrees of freedom. That's where that middle is going to be. So when we have the degrees of freedom of 4, that's where the mean ends up being. Degrees of freedom of 8, that's where that mean ends up being. Okay? For anything greater than 2 in degrees of freedom, the mode peak of the chi-squared density curve is at degrees of freedom minus 2. We'll get to that later. When degrees of freedom is 8, for example, the chi-square distribution has a mean of 8 and a mode of 6. That's what the mode would be. It's always skewed right. Theoretically, it could look a little more normal the higher the number of degrees of freedom. But because it always starts at 0, it's going to have that skew look. Okay? So let's go back to our example here. Let's check these conditions. So then we'll get into what this formula is. For our conditions, number 1, do we have a random sample? Of dice rolls. Yes, it was stated. I think it was stated that. Yeah, I mean it doesn't say that, but you're just rolling dice. It's not like there's no way you could not have. We'll say it's implied. A random sample of that. We need to check if all the expected counts are greater than or equal to 5. So all expected counts greater than or equal to 5. Yes, and you should check that. So, and you should note at least the lowest. So it's important to note the lowest. Lowest is that 90 times 1/6 equals 15. That's the lowest. All right, and then, which is greater than or equal to 5. And then the last one is the check for independence. We had 90 total rolls. Is 90 less than or equal to 10% of all possible rolls? Absolutely. You could have an infinite number of rolls, so that is a yes as well. So our conditions happen to be met. Now we need to get into this. It's called a chi-square goodness of fit. You can abbreviate GOF test. All right. Now the actual formula, which I'm going to show here, looks like this. Chi-square statistic is a measure of how the observed counts, how far the observed counts are away from the expected. So we're trying to see if it's close enough where maybe it is fair and it's just a little bit of sampling variability, or not. So chi-squared is equal to the sum of the observed minus the expected, and we do squared because we don't want any negatives, and then we divide it by the expected. And we actually divide it by the expected because, like, maybe the observed minus the expected is 5 for two different distributions, but it's out of a totally different number of expected, which changes that value, that whole statistic a little bit. So think of chi-square as a measure of the distance of the observed counts from the expected counts. And like any distance, it's always going to zero or positive. We want it to be zero or positive, so that's why we square them. Larger values of chi-square are stronger evidence to reject, essentially. And small values of chi-square suggest that the data is consistent with what we were expecting with the null hypothesis. So typically we're looking at an alpha level of like 0.05, just like we would with other values, other tests, and we can compare to see if it's actually significant or not. But make sure you have this formula right now. We're going to use that now. And again, just a reminder, this is the sum of all of them. So we have to find each individual observation minus the expected, square it, and divide it by the expected. Do that with the next one, and add them all up. So you're either going to have to make a table of values or use your calculator smartly. So for this chi-square goodness of fit test, because the formula is observed minus expected squared divided by the expected, ultimately we're going to be plugging in, sorry, the sum of that. I didn't even put the sum of that in there. Oops. We were going to have to show each individual one. So we had 12 for the first one, all the way to 15. So 12 minus the expected of 15 squared divided by 15 plus all the way to the last one, which is 15 minus 15 squared divided by 15. Now, I'm not going to write all that out. You can use each individual one on your calculator, or you can use your tables. I'm going to pull that up here. So that's another way you can do it. So I have the observed in list 1, the expected in list 2. So list 3, I might put in parentheses observed minus expected. So list 2, oh sorry, observed. So that should be list 1. List 1 minus list 2 squared divided by the expected, which is list 2. Let's see if it gives me all those values. So it does. So what I can do is I can find the sum of all of those. I can either add them up by hand, or I can go back and I can hit second stat, go over to math. One of the options is sum, so that's 5. I can do the sum of all of list 1. Sorry, that was list 3 then that I had all those in there. And I can get my sum as 14.4. So somehow I got to get that value. That is a 14.4, and that is my chi-squared value. Okay? Now, is that a big value? Well, we either have to go to my table, which is table C on your formula sheet, And what I can do is I can find 14.4, but it's the degrees of freedom of 5. So it's number of categories minus 1. So if I go back here, the number of categories are 6 of them. There's 6 different possibilities. So degrees of freedom would be 6 minus 1, which is 5. So I need to then go find degrees of freedom of 5. We're working in this specific one. And we want to find the closest to 14.4, which is kind of in here. So it's going to be between 0.01 and 0.02. Now that only gives you a range in this route, so you can go to your calculator. We have learned ways to find a p-value. Now we can go down to number 8, which is chi-square CDF. Click that. Our lower, because we're going to try to find the extreme. So our lower is going to be 14.4. Our upper is going to be infinity. Degrees of freedom we said was what? 5. Should give you about a 0.0133. Okay, so it is between 0.01 and 0.02, but our p-value for this would be 0.133. Now, just like with any other thing, that is a low p-value. And we would have to reject. So because 0.0133 is less than, we'll just say 0.05, or any reasonable alpha, because I don't think we stated an alpha level, so we're just going to stick with 0.05. We reject H naught, which means we have convincing evidence that essentially for the alternative, all die outcomes are not equally likely. And you can say you believe that this, I can't even spell likely there. You can say that you believe that this is not a fair die then at that point. Okay? So, one other thing I want to point out from the calculator before I let you go here. There is, now that we've gotten to this point, tests, and there is a chi-square goodness of fit test, but I don't know that every calculator has it. If yours has it, you can find it has to be the goodness of fit test. My observed was in list 1, my expected was in list 2, and my degrees of freedom would be 5, because 6 minus 1 is 5. And if I calculate it, it does all that work for me. Chi-square is 14.4. The p-value is 0.0133-ish. That is there. Now, we'll get more into this contributing values there, but that's all of, I guess, basically what that bottom part is. You can go over to the right to see all of them. That's all of the individual things that you would add up. So observed minus expected squared divided by expected. That's all the things that added up to get 14.4. So those are considered the contributions. That is chi-square goodness of fit in a nutshell. I know there's only one full example, and we'll get to some more. But I guess I do want to just briefly show you another one that might fit with chi-square, that definitely does fit. Let's see, like this one, okay? So like if you're looking for, this has all the animal crackers in a bag of animal crackers. We're expecting them to be uniformly distributed, so you could find the expected ones. But from our example, this is what was given. And you can compare then, see if it's significantly different than what is expected. Another example, Reese's Pieces. It doesn't have to all be equally likely, Hershey Company makes Reese's Pieces, and they say that there's going to be 50% orange, 25% brown, and 25% yellow. So if we have this sample of 80, the counts that were given, these are the observed counts, are not necessarily the same as the expected. If you're expecting 50% orange, you'd expect 40. That's that half of the 80. And 20 of these and 20 of these. So clearly the exact, like the counts are off from our sample, but we need to do this goodness of fit test to see if they're off by enough. I think I have one that's unique because it gives you an extended ratio, 2 to 2 to 3 to 3 to 4. That's the ratio that it should be for this, based on residents in the area, how they play at use these parks. And if we know, I guess I didn't even add up, we have a total, I did add them up. So the total number of residents for all of that should be 2264. So what you can do, if you add all those up, 3 plus 3 plus 2 plus 2, that's out of 14. To find the individual expected counts, so we have our observed and our expected. Your observed were given. So 323, 353, 445, 465, 678. To find the expected, you'd have to say, all right, that first one should be 2. It's part of the 2. So I'm looking right here. That's 2 out of the 14 times the total of 2264. 2264. That would get us that expected count. Okay. For this one, it's also 2. It should be 2 out of 14 times 2264. This one has 3. So we'd have 3 out of the 14 times 2264. We'd have the same thing here. 3 out of 14 times 2264. And the last one would end up being that 4 out of 14. So that's how you can find the expected counts if you're given certain proportions. But then you'd run the same sort of test. It's a goodness of fit test. We're checking the observed compared to the expected. All right? So that is section 12.1 on chi-square goodness of fit tests. See you next time.